G'day, in this video we're going to be starting Module 8 from the universe to the atom. And the first topic that we're going to be looking at is exploring evidence for the electron and in particular focusing on cathode ray experiments. We're actually starting inquiry question 2 first and skipping inquiry question 1 for the moment. The first inquiry question builds on concepts that we learnt about in Module 7, particularly around spectroscopy and observing space. This inquiry question builds on those ideas, focusing on explaining how our universe came to be and processes that occur within the universe. However, we're not going to dive into that straight away because I feel as if we're going to be able to appreciate a lot of the nuance in those topics once we have a deeper understanding of the atom, which is the focus of inquiry questions 2 to 5. Therefore, we're going to be moving through our understanding of the atom and picking up elements of inquiry question 1 about the broader universe as we learn about concepts which are relevant, particularly in inquiry questions 4 and 5. Inquiry question 2 focuses on breaking down the atom into smaller parts, protons, neutrons, and electrons, which we're already familiar with. We've been applying our understanding of these subatomic particles throughout the course, as this is core knowledge taught in years 9 and 10. However, inquiry question 2 is more so looking at the how. You already know of their existence, but historically what was done that led to their discovery. A good chunk of the content in Module 8 is all about the history of the discoveries that led to our modern understanding of physics, and we start here at the electron. Dot point 8.2.1 is all about investigating experimental evidence which supported the existence and supported the properties of the electron. Today we're focusing on cathode rays and Thomson's charge to mass experiment. So through this lesson today, I want you to be able to understand the conclusions made from early experiments with cathode rays, and together we're going to investigate the methods used by J.J. Thomson to determine the charge to mass ratio of a cathode ray, and then also have a little bit of a discussion around the scientific contributions made by the work of Thomson. So our early cathode ray experiments occurred in the late 1800s. It was at this time that vacuum pump technologies had significantly improved, which gave people the capability to construct new apparatus that would enable experiments to be conducted in low pressure or vacuum conditions. One of the apparatus which was built was a cathode ray tube. It makes a beam of electrons, except the people making the cathode ray didn't know what this cathode ray was. They didn't know the identity of the electron in the first place. Today, we know they're a beam of electrons. In any case, the scientists who worked with these cathode rays were the first people to work towards the discovery of the electron itself. William Crookes was the first person to develop a cathode ray tube in the 1870s. You may also hear the term Crookes tube be used to identify a cathode ray tube. It is aptly named after him, the person who developed it first. The way that it would work is that you would have a low pressure tube, glass tube, which contained a cathode and anode, a negative and positive terminal respectively. The anode and cathode were connected to a high voltage supply, such as an induction coil. And this high voltage supply provided enough energy for electrons to be able to travel through empty space towards the positive anode from which it was attracted to. Without the high voltage, the electrons would not have the capacity to be able to bridge this gap. It should also be noted that a near vacuum is required in this situation because otherwise the air particles in between the anode and cathode would interact with the electrons, causing resistance. So once cathode rays were being produced, scientists then did everything that they could to try and experiment with them. They didn't know what they were, so they had to go about trying to identify. It's figured out pretty quickly that cathode rays cause fluorescent materials to light up, just like we've got here. This fluorescent screen interacts with the cathode rays as they pass and makes the screen fluoresce. This allowed scientists to actually see the rays that they were working with, making them better able to observe phenomena and demonstrate the properties of these cathode rays. In this early experimentation as well, scientists tried to change the materials of the cathode and noticed that it didn't matter what metal they used for the cathode, the same rays seemed to be produced. Scientists also discovered that cathode rays were able to cast shadows when they came into contact with a solid object. Classically, this is done with a cross shape known as a Maltese cross. What you'll notice in this experiment is that cathode rays are able to pass through the tube and do so by traveling in straight lines. This is demonstrated by the shadow that is being cast by the Maltese cross, and also demonstrates that the cross is able to absorb the impact of the cathode ray, so to speak. These kinds of observations seem to suggest that the cathode rays behave like light does, therefore indicating that it has wave-like properties. Scientists also experimented with cathode rays by applying electric and magnetic fields to them, and when doing so, noted that they deflected. In particular, they deflected in the same direction which would be consistent for a negative particle. They were attracted to the positive terminal of electric plates, and when in the presence of a magnetic field, the cathode ray deflected in the direction opposite to what would be predicted for a positive charge by the right-hand rule. As waves don't have charge, scientists concluded that this evidence suggested that cathode rays were indeed particles, and charged particles at that. Scientists also noted that when cathode rays came into contact with matter that was able to freely move with very little resistance and only requiring very small amounts of force to allow movement to occur, they noticed that the cathode ray was able to interact with this material. A classic example is a paddle wheel suspended across two parallel wires. When the cathode rays come into contact with the paddles that are on the wheel, torque is generated. And because the force is being applied away from the axis, a fairly large torque is produced relative to the force of collision. On top of that, the paddle wheel has very little contact with the parallel wires, significantly reducing friction. As a result, the cathode rays are able to transfer momentum into the paddle wheel and make it spin quite fast. Because there was a transfer of momentum from the cathode rays to the paddle wheel, scientists again found a piece of evidence which suggested that the cathode rays were indeed particles. This is because particles have mass and momentum and not waves. With these experiments, there was evidence to suggest that the cathode ray was a charged particle, but also an electromagnetic wave. While today we know that these cathode rays are electrons and therefore charged particles, during the late 1800s when these experiments were occurring, there was a lot of debate amongst the scientific community. There were definitely strong arguments in both directions, and the fact of the matter is there was no conclusive evidence to shift sentiment in the scientific community either way. So in comes J.J. Thomson. He looked to design an experiment which would hopefully prove that the cathode rays had mass and therefore were particles. He took everything that the scientific community had already learnt about cathode rays, charged particles, and generally Newtonian mechanics to make an experiment to figure out the charge to mass ratio of the cathode ray. Being able to consistently measure a charge to mass ratio for the cathode ray would suggest that the ray not only had charge but also had mass, and therefore would confirm the cathode ray to be a particle. So, how did he do it? Thomson sought out to create a cathode ray tube which could produce a very fine beam of a cathode ray, while being able to selectively apply an electric and magnetic field, both of which he could adjust the strength of. If neither the electric plate or the magnetic field was on, the beam of cathode rays would travel directly straight. If only the electric field was on, the electrons were deflected towards the positive plate. And if only the magnetic field was on, the magnetic field would deflect the cathode ray in the exact opposite direction to the electric field. As such, as shown in the diagram, there was a force being applied to the cathode ray in the upwards and downwards direction. By adjusting the strength of the electric field and the magnetic field, he was able to find a sweet spot in which he could balance out the two opposing forces and still have the cathode ray travel in a completely straight direction while under the influence of both fields. What this suggested was the applied force of the electric field and the magnetic field were equal and opposite. Once he'd calibrated both fields, he then turned off the electric field to then only analyze the trajectory of motion caused by the magnetic field. The design of this experiment was based on Thomson's idea that if he knew the electric field strength, the magnetic field strength, and the radius of the arc formed by the deflection of the cathode ray in the magnetic field only, then he would be able to determine the mass to charge ratio of the cathode ray, and therefore prove that the cathode ray not only had charge that was negative, but also had mass. What were the quantitative principles that enabled this to happen? In a scenario where Thomson applies an electric and magnetic field, which exert an equal and opposite force on the cathode ray, we can conclude that the force due to the electric field is equal to the force due to the magnetic field. According to our datasheet, electric field forces are equal to QE, the charge of the particle experiencing the force multiplied by the electric field strength. And the force applied by a magnetic field is equal to QVB, the charge of the particle experiencing the magnetic field force multiplied by the velocity of the particle multiplied by the magnetic field strength. By dividing both sides by Q, our charges cancel out. And from here we can write an equation for the velocity of the particle, which is equal to the electric field divided by the magnetic field. It should also be noted that the force due to the magnetic field is actually equal to QVB sine theta. But because in Thomson's experiment, theta is equal to 90 degrees, and it's been done so on purpose, that means sine theta is equal to 1, and therefore QVB sine theta is equal to QVB. In step 2, Thomson only analyzes the deflection caused by the magnetic field. This deflection will lead to a centripetal force causing circular motion. Therefore, we can conclude that the force in this scenario, which is the force of the magnetic field, is equal to the centripetal force experienced by the cathode ray. This can be written as QVB is equal to mv squared on r. Again, technically the formula for magnetic field strength is QVB sine theta, but again, theta is equal to 90, therefore sine theta is equal to 1 and can be neglected in this solution. You'll notice that this equation has Q and M, the charge and mass of the cathode ray. Therefore, we can solve for Q on M, the charge to mass ratio. This can be done by dividing M to the other side and dividing V and B to the right-hand side. One of the V's cancel, leaving us with Q on M being equal to V on BR. Now, measuring the velocity of the cathode ray can be quite difficult, which is why step 1 was so important, to first balance out the magnetic and electric field forces. In doing so, we now have a statement for velocity, which is E on B. By substituting in, we can get that the charge to mass ratio is equal to the electric field strength divided by B squared multiplied by R, the radius of the arc through which the electron is moving. And as such, the statement that we looked at earlier stands true. If we know the electric field strength and the magnetic field strength, which was applied to balance out both forces and make the electron travel in a straight line, and we turn off the electric field and only apply the magnetic field and measure the radius of the arc formed by the cathode ray when it's deflected by the magnetic field. In other words, if we know E, B, and R, then we are able to calculate for the charge to mass ratio. Upon repeated experiments at all sorts of different magnitudes of magnetic and electric fields, Thomson found that he could get a consistent charge to mass ratio of 1.76 times 10 to the 11 coulombs per kilo. This proved beyond doubt that the cathode rays had mass and therefore led to the agreement among scientists that cathode rays must be particles as they have mass, they cannot be waves. Furthermore, as scientists already knew that cathode rays could be ejected from all materials they used as a cathode, this supported Thomson's development of a new atomic model, the plum pudding model, which was an improvement of the current model, Dalton's billiard ball model. Dalton's model originally stated that atoms were simply spherical and indivisible, and they were made of uniform matter. However, Thomson's plum pudding model suggested that there were particles smaller than the atom with a negative charge that could be dislodged from the atom itself. What that suggested was that atoms were still spherical, but came in chunks and parts. Thomson suggested that the atoms had small negatively charged particles, which were generated through the cathode rays, and they were suspended in a sea of positively charged matter with a low density. This model was able to account for the size and density of atoms and the fact that a lot of matter had to be distributed over quite a large space. This charge to mass ratio, while Thomson didn't know the exact charge or exact mass of those particles, he did know that they had a lot of charge compared to their mass. The charge to mass ratio was 1,800 times greater than the charge to mass ratio for a hydrogen ion, which is a proton essentially. While he couldn't prove it conclusively, he made the assumption that the two particles had the same charge, but the electron had 1,800 times less mass than the hydrogen ion. This assumption was proven to be true experimentally later, and actually will be the topic of our next video. And interestingly, this experiment relied on Thomson's mass to charge ratio in order to figure out the mass in the first place. The two experiments do go hand in hand, And the conclusion of the mass and charge of the electron could not be done without the other. Now, while this model was imperfect and didn't give us a full understanding of the atom, for 1897, it was a pretty good experiment and brought us much closer to identifying the electron and our understanding of subatomic particles. In the next video, we're going to be looking at further evidence of electrons, in particular, how we determine the charge and the mass of the electron through Millikan's oil drop experiment. But until then, have a good one.